Hello. In this video, we're going to look at some kinematics problems, that is, problems that have to do with rates of change, speed, acceleration, that sort of thing. So first, we're going to distinguish between two different kinds of rates of change. So if we're looking for an average rate of change, we're looking for a slope between 2 points, basically. So a slope between points where we have actually a change in distance over a change in time, for example. So delta y does not equal 0. Delta x does, well, delta y might equal 0, actually. Delta y may or may not equal 0, but the important thing is delta x does not equal 0. Normally, when we're dealing with kinematics problems, that would be a delta t does not equal 0. We'd be dealing with rates over time. So our denominator isn't 0. An instantaneous rate of change is a slope at a point. So in other words, when delta x does equal 0, or delta t does equal 0, depending on the variable that we're using. And that, for this, we would use the derivative. All right, so when we are being asked to determine the instantaneous rate of change of the volume of a cube with respect to the length of a side, that is telling me my independent variable. So I am looking for the rate of change of the volume, so d volume, with respect to the length of a side, so dv ds. So I need a relationship between volume and the length of a side. So it's a very straightforward example here because the volume of a cube is its side length cubed. So dv ds is going to be 3s squared. So the rate of change of the volume with respect to the length of the side is 3 times whatever the side length happens to be at that moment squared. So if I wanted to then know what is the specific rate of change for a particular length of side, so if I'm imagining that this side length is increasing or decreasing, the volume is also going to be increasing or decreasing. And the relationship is going to be 3 times the side length squared at any given moment. So if my side length, for example, is increasing at a constant rate where it's 1 centimeter being gained every minute, at the moment that that side length is 1 centimeter, then the volume is gaining 3 centimeters cubed per minute. And at the moment when that side length is, let's say, 2 centimeters, then 2 squared times 3 would be 12, so the volume is increasing by 12. So this is an increase in the volume not with respect to time, but with respect to side length. More commonly, we're dealing with changes with respect to time. So let's, oops, not sure what's going on here. It's not going to scroll. There we go. All right, so let's say we have a formula here that relates the surface area of a layer of a oil spill that is being given by this formula, A equals 30t cubed plus 100t in minutes. So for every minute after this oil spill, the area is given by this function. Now we want an average rate of change of the area as a function of time for the intervals from 2 minutes to 3 minutes and 2 minutes to 2.1 minutes. So let's go with the 2 to 3 minutes first. Obviously, between 2 and 3 minutes, delta t is equal to 1 minute. I am also going to need delta area. So for the change in area, I need the area at 2 minutes, and I need the area at 3 minutes. So substituting in area equals 2, so we've got 30 times the 2 cubed plus 100 times 2, and we get 440. Oops. Oh, I haven't given you units for the area, did I? Let's go in meters squared. All right, so 440 meters squared. And then if I do this same calculation with 3 instead of with 2, I get 1,110 meters squared, which means that delta A is going to be the difference between those, so 670 meters squared. So at this time, the average rate of change is going to be 670 meters squared per minute. That's between 2 and 3 minutes. That's the average rate of change. If I take from 2 to 2.1 minutes, this is going to be closer to instantaneous because it's a smaller time interval. Delta t equals 0.1 minutes. I already know that the area at 2 minutes is 440. So let's find the area at 2.1 minutes. So if I calculate this, I get that that is 487.83 meters squared. So when I subtract the 440 to figure out delta A, I find that delta A is 47.83 meters squared, which means that the average speed or the average rate of change here, 47.83 divided by 0.1, is 478.3 meters squared per minute. So the average rate of change is very different depending on the interval that I choose, but both intervals started from 2 minutes. What this tells me is that this is probably growing more rapidly as time goes further on. But if I want to find the instantaneous rate of change as a function of time at 2 minutes, for this I want the derivative. Now, again, I could use a limit. I mean, we've just been sort of seeing the approach here. I'm expecting my answer to be closer to the 478 than to the 670, but I need the derivative here. So I need dA dt, which is going to be 9dt squared plus 100. So then dA dt at 2 minutes, when t equals 2, is going to be 90 times 4 plus 100. So that is going to be 460 meters squared per minute. So yes, quite a bit closer to the 478. And that does imply that this rate of change is getting faster as we move between 2 and 3 minutes. And that tells me that at 3 minutes, I'm expecting the rate of change to be quite a bit higher than the 670. So be very clear on whether your question is asking for an average rate of change or an instantaneous rate of change. So let's look at another example here. The position in meters at time t in seconds of a particle is given by this function here, and we want to calculate its speed. So in other words, ds dt, so the change in its position over time. When its acceleration is 0, that's at a particular moment, so this is an instantaneous speed. But acceleration is going to be the second derivative of position with respect to time. So I want to first figure out when is its acceleration 0 and then go backwards to figure out speed. But to answer this question, I'm going to need the first and the second derivative. So s prime of t, which is the velocity function, is going to be 6t squared minus 96t. So then the second derivative of that is going to be the acceleration function. That's going to be 12t minus 96. So I want to know when is the acceleration equal to 0. So when is 12t minus 96 equal to 0? And that is going to be when t equals 8. So now I want to know what is the velocity, what is the speed at 8 seconds. So the calculation that I need to now do is figure out the velocity at 8 seconds. So 6 times 64 minus 96 times 8, and we get negative 384 meters per second. Now, because the question just asks for speed, you would get away with not including the negative 384 here. Velocity has a direction, whereas speed doesn't, and the question isn't technically asking for the velocity. And so you wouldn't need to include the negative, but it certainly doesn't hurt to include it. So at the moment when the acceleration is 0, the velocity of this particle is negative 384 meters per second.